Hello. We are pleased to welcome you to this webinar on electric drive NVH engineering. In this webinar, we will give you an overview about our Siemens SimCenter simulation and testing solutions around edrive development and edrive engineering for NVH, and also give you some of our engineering services experience and examples. The webinar will be given by Jonas Verhoeven and myself. Jonas is a product manager in our SimCenter 3D product team, and he is dealing in particular with transmission applications. I'm François Gérard. I'm working in the engineering services team and responsible for our portfolio of services. The agenda for this webinar is as follows. We start with an introduction about the challenges of edrive engineering and the challenges of the edrive NVH engineer. And then we will go through the different stages of the edrive development, early stage, detailed design, until vehicle integration, in order to give an overview of how to deal with NVH and our solutions and examples there. Let's start with an introduction. And looking at the high-level challenges of edrive engineering, NVH comes as one of the first points in that electric drives are not silent and have a very specific noise characteristics, higher frequencies due to the construction of the electric motor and the transmission, tonal content, and phenomena such as the switching frequencies from the inverter can be very annoying, despite the fact that the overall levels of the e-powertrain are limited compared to traditional powertrains. Of course, there is a lot of other challenges in terms of performance and in terms of thermal management, how to deal with all the losses. And of course, vehicle integration is also very important. And we would like in this webinar to go beyond just NVH, but also show how can we deal with NVH, considering also the other attributes like performance and thermal. How do we manage the need to deal with all these attributes? So looking at the traditional development process, what we still see a lot in companies is the trend to have siloed teams, to have separated teams dealing with the different attributes of the vehicle, dealing with NVH, dealing with thermal, dealing with the physical testing and with vehicle integration. So that is not ideal because it leads to a longer development cycle, and also the fact that we solve issue for one attribute, and this is going to create a problem on another attribute if not done carefully, and this all leads to a lot more iterations in the design. What we propose here is integrated development process or workflow, which allows to deal with all of these attributes together. So the idea is to keep a consistency through the development cycle between these attributes, have the ability to assess each of these performances as early as possible, and allows teams to work in parallel and together, shortening the development cycle overall. This is what we refer to as multi-attribute balancing. We try to give some examples of that. The overall framework which we use is shown here. We have below the main stages of the edrive development, from requirement definition, architecture and sizing, the engineering of the different parts of the powertrain, and then the integration and the control validation, the V&V steps. What we see above is more the edrive design process. So the product lifecycle management aspect, how do we define the requirements and how do we develop the edrive system by looking at all these attributes and also integrate it with the requirements that we can track along the development cycle until the final verification and validation of the product. So this offers a framework in which the simulation and testing activities are well integrated with the product design, and we can leverage simulation and testing as much as possible along the development cycle. We will use this framework to go through the edrive NVH development journey. But first, let's look at the main challenges a little bit more into detail. The challenge of the NVH engineer. Overall levels are lower, but as discussed before, we have these high frequency signals due to the e-motor construction or the transmission and the gear interactions. And we have also quite specific phenomena like this switching noise from the inverter, which leads with the off-zero orders, like we can see here. So very specific noise phenomena, which are also very annoying because it's about high frequencies and very specific signatures. So although we have overall lower overall level, we have to deal with these phenomena, and we have to make sure that these noise signatures stay below, let's say, the level of road noise or aerodynamic noises. If we look into a bit more detail into the development cycle, we are going through the different phases here and looking in particular at NVH. So first, the requirements need to be defined at the vehicle level in terms of NVH. This can be done, for instance, by looking at predecessor vehicles, by looking at competitor benchmarking, which are activities which we also do in our engineering services team. And starting from that, we can go through the concept definition of the electric drive. So at the concept stage, we define the architecture of the system, the transmission layout, the type of e-motor and construction. So already in that early phase, we can perform some NVH analysis in order to understand the impact of design decisions on NVH. In the detailed design stage, for each component, the e-motor, the inverter, the gearbox, we are going to do more and more detailed predictions as more details on the construction become available. So we can start optimizing the NVH while keeping performance and thermal on target. For the gears, especially the gear geometry and microgeometry are being defined, and we are also looking, for instance, at the gearbox housing, how to make sure that it is not going to create a high noise level or amplify the excitations into high noise levels. In the integration stage, we are still looking at balancing the different performances, including NVH, and also starting to do vehicle level NVH assembly in order to assess what the NVH performance will be once integrated in the vehicle. Finally, in the last stage, we will start doing more and more testing, although testing will support the whole process from the start. But here we start to have the system available for testing. We can do also model-based testing, including simulation model and physical system. And we will look at the performance. We can also predict the noise and experience the noise in a NVH simulator. We can do sound quality analysis and also controls fine-tuning, looking at the NVH impact. So let's start looking at the simulation in early stage, in particular for the electric motor. What we propose here is an approach which is basically a systems engineering approach, but for the NVH performance. So the electric machine noise and vibration app, which we call eNoise app, is an application within our system engineering software SimCenter AIM-Sim, which deals with the NVH performance of the electric drive. So it allows, in a systems engineering environment, to create a model of the eDrive and to integrate there also its vibroacoustic performance. Typically in the early design stage, we don't have much details about the construction. Maybe we have the type of motor, we have a first idea of the geometry, the number of poles, and the basic design of the electric machine. This will allow us to predict the electromagnetic loads, or the B fields, in the air gaps. We will then use some basic assumptions about the structural parameters of the electric machine in order to be able to predict the noise radiated from these electromagnetic excitations. So here we see, for instance, some assumptions which we do about the geometry. And this will allow us to predict the vibration, and then we will make a free field assumption to have a quantification of the noise level from the e-machine from the very early stage of the design. The process looks like this. First, we have a pre-processing step where we create what we call a reduced order models, basically using typically 2D electromagnetic FE simulation. We create the maps of these B fields or magnetic fields in the air gaps in different conditions with different torques, for instance. And this is the data which we will use as input to our system engineering software and simulation. We will use these loads and combine them with our analytical, structural, and acoustic models in order to come up with order cuts with system level NVH predictions. There is a possibility to replace the analytical model by a more detailed FE model. This is what we call vibration synthesis, which is typically only possible in later stages of the development. So we are going to come back on that later in the presentation. An example here, we are using this system simulation capability to evaluate the effect of controls on NVH, in particular for the pulse width modulation, so basically the switching noise frequency from the inverter. We have our inverter model here, the controls which are defined as an input, and this is all integrated in a full vehicle model, a basic full vehicle model. And here we see, for instance, A to B comparison about the impact of control strategy on the NVH. Basically, we do try to spread the frequency content of the excitation and to avoid pure tonal excitations. So through this method, we can see that we managed to reduce the peaks in the response, so that is very positive. But on the other hand, we can also see that the background is more important. So we have, let's say, an excitation across the frequency range, which leads to this background noise. So the message we want to give is that it is possible in early stage to already assess the impact of the control strategy on the NVH. Now we will discuss about the transmission part, and Jonas will go through this simulation capability on the early stage for transmission.
Yes, thank you, Francois. So I'll talk about NVH performance engineering in early stage, but focused on the transmission. Now, before I do, I want to take a step back and first talk about what are the typical challenges that we see in the area of transmission engineering. So first of all, we see that NVH engineering has a limited influence on design. So typically NVH performance, let's say prediction and validation, is done later in the development cycle, which means that engineers only have design responsibility on housing geometry or bearings or on the gear macro geometry. Well, if you would like to optimize NVH performance, you typically also would like to change the transmission design itself. Secondly, we know that the system compliance will have a big impact or influence on the gear contact detection and therefore also on the NVH performance. So how to consider really that coupled effect between the gear contact detection and the full transmission system level effects. Also, when optimizing transmissions for best NVH performance, it will affect strength and durability performance attributes. So you need to make sure that once you optimize your transmission, that it also meets these other performance attributes. And then finally, you would like to optimize transmissions for both driving in slow speeds in city environments at high speeds on the highway, which means that you basically need to optimize your transmission for a broad range of operating conditions. So what is the traditional process that we see today for transmission engineering, especially early in concept stage? So typically you start from your transmission requirements, which can be the desired gear ratio, the desired power conditions, and the available space. And typically you then optimize the transmission for certain targets on durability, strength, efficiency, and NVH. So the first step is optimizing the layout, which means optimizing the positions of the shafts, the gears, the bearings, and their corresponding dimensions. Once you have your layout fixed, you go into bearing selection, bearing optimization, and bearing rating. And then finally, similar for gears, you start to optimize both macro and micro geometry and evaluate the different performance metrics. But as you can see from this process, it requires many iterations and optimizations, typically at subsystem level, which means that it's not only a very intensive manual approach, but it's also very time consuming. But I think even more importantly, it means that if you optimize at the subsystem level, it doesn't mean necessarily that you find the overall optimum design. And that is why with SimCenter tools, we would like to propose an alternative approach where typically you also start, let's say, from your layout and bearing optimization, but then you use a systematic approach to optimize both gear macro and micro geometry at the same time. And the advantage is really that you have a systematic or automated approach to find the global optimum design, at the same time considering really your full transmission system level behavior. Again, it's important that you take into account the influence of the transmission, of the compliance of the transmission, the housing, on the gear contact detection when optimizing your gear geometry. So our colleagues from the services organization also developed a process to perform this layout optimization using SimCenter tools, more specifically SimCenter Heats and SimCenter 3D Motion. And here the target is really to optimize your layout or your topology for minimized mass and minimize misalignment variability. Why misalignment variability? It's because it's a good indicator or it's a good strategy to later on optimize the microgeometry. Because if you minimize, let's say, the variation of misalignment in function of torque, it typically also means that you can optimize your microgeometry across a wide range of torque conditions. What is the input? It's typically your gear requirements, like the gear ratio, max torque, max speed, but then also constraints on stress, etc. What is the outcome, or what are the variables? It's the design parameters related to positioning, to layout optimization. So really the shaft, gear, and bearing positions together with the shaft and the gear dimensions. And so a good layout is basically the starting point for a good transmission NVH optimization. I've already talked about gear design optimization. Gear design optimization is really a framework leveraging SimCenter 3D motion and SimCenter heats to optimize gear macro and microgeometry in terms of different KPIs, such as durability, efficiency, and NVH. Now, the key here is that you really consider a sophisticated optimization algorithm to optimize your transmission within a minimum evaluation time. And why is this important? For example, let's consider a two-stage lay shaft transmission, which is very common for EV passenger cars today. If you only consider those two gear pairs, we're already talking about more than 100 design parameters. So if you would like to find an optimum design for such a large design set or design space, you really need a robust algorithm, an efficient algorithm to find that optimum design within a minimum evaluation time. Also very important is that when you optimize your gear macro and microgeometry, that again you consider those system level influences. So what is really the influence of the compliance, of the deflection, and therefore misalignment on your gear contact behavior. And then secondly, also the fact that you would like to consider multiple operating conditions, which means typically multi-torque conditions. And then finally, these designs or this optimization that you typically do, let's say early stage, you would also like to then verify and validate in more detailed design. So making sure that your transmission meets the NVH performance requirements that you have targeted. So what does the typical process look like when we talk about gear design optimization? So targets are more NVH focused targets where we would like to minimize your peak-to-peak transmission error, for example, or minimize your bearing force harmonics. Whereas the input is typically that layout that you've optimized from that first part, and then constraints again on max torque, max speed, constraints on stress, strength, and durability. And the variables are here really your gear macro and microgeometry variables. And so, of course, here the goal is to optimize the gear geometry for best NVH performance, but at the same time making sure you also meet, for example, criteria on root stress, on contact stresses, flash temperatures, so more the let's say the strength and durability and efficiency type of KPIs. And with that, I'll give the word back to Francois.
Thank you, Jonas. Let's now get back to our agenda. And we are going now to focus on the detailed design phase. In this phase, we are able to do much more detailed simulations in order to understand the NVH performance of the electric motor, the inverter, and the gearbox in much more detail, and also continue assessing the effect from controls. So the key will be to optimize the e-motor NVH while keeping performance and thermal on target in our effort to ensure multi-attribute balancing. We will also go into more detail in the definition of gear geometry and microgeometry and start optimizing the housing of the gearbox. So the process for a detailed analysis of e-motor NVH looks as follows. In the first step, we need to identify the loads. by means of a 2D or 3D electromagnetic FE model. We will characterize the magnetic field and the loads which are applied to the stator of the e-motor. Could be using different tools, like for instance, electrical machine design and magnet. And these forces, these input, are then mapped onto a structural model of the stator in order to predict the deformation and the vibrations of the stator. From there, we will assess the vibrations, and we will then evaluate the vibroacoustic performance of the electric motor. This can be done for different conditions like stationary, fixed RPM, or run-up, run-down with different torque conditions, and so on. One important thing here is to have a good representation of the e-motor structure. Indeed, the electrical motor is typically a nonlinear structure and not, let's say, a very easy structure to model with a finite element linear solution. We have a lot of experience in our engineering services team that we gathered by doing a comparison, correlation of the e-motor structural by means of testing, correlation between testing and simulation, which allow us to improve the assumptions and identify the best practices in order to simulate the structural vibrations. In addition to that, it remains possible to understand the effect from controls on the NVH performance. As in this example, we are using an AIM-SIM system level model of the e-motor, in which we can input different inverter current waveforms as input for the electromagnetic simulation. So we are closing the loop with the controls. Now, besides these, let's say, very detailed calculation, one of the, let's say, difficulties to deal with will be a calculation time, because we are talking about quite large models. So in this case, we can propose our eNoise app as a solution, and in particular, the so-called vibration synthesis method. In this method, we are reducing the FE representation of the structure by means of a reduced order model. And this will allow us to do much more fast predictions. We will need, in a first step, to pre-process the information to identify basic mode shapes from the e-motor structure, and then we will calculate the response as a superposition of these basic mode shapes. So this allows us to use the same approach we described before with a more realistic representation of the structure instead of an analytical model. This is currently an option offered by our services, and this is coming up in our SimCenter 3D product. Here, some other considerations. The edrive engineer will look for options to optimize the performance, and for instance, skewing of the e-motor or notching strategies can be used in order to optimize the performance, but they also have an impact on NVH. So these are important parameters to take into account. In this overview, we show the possibility to evaluate the effect of skewing or notching strategies on the NVH performance by using our eNoise app. So this will allow to do a quite fast prediction and understanding impact of skewing and notching, and be able, let's say, to assess not only how they will affect the performance, but also how they will affect the NVH of the e-motor. Now, still looking at the need to come up with a well-balanced design, which will lead to good performance from a thermal viewpoint, from a durability viewpoint, from an NVH viewpoint. This is an example of a workflow we can propose to do this optimization and properly take into account the different attributes. So our engineering services team is supporting customers to implement and deploy our SimCenter simulation solutions into a workflow which is suited to the customer organization or process. In this case, for instance, assessing the electromagnetic performance, calculating the NVH, assessing the rotor stress, and then doing a check on the thermal performance, and in a suitable way, iterating through this performance until we come up with a balanced design. So here, the key is multidisciplinary analysis and optimization. We are using, for instance, heats as an optimizer to realize this workflow. Looking at the transmission NVH, also in this detailed design stage, we are going to be able to look much more in detail at the impact of the construction on NVH. For instance, we can capture the coupling between the system level dynamics and the deformation on the shaft on the gear contact. We're able to consider the influence of damping. We can also simulate phenomena linked with NVH holes, as we can see in this picture, which will generate specific harmonics in the response, and as we see here, can cross resonances and lead to higher noise levels. We can also look at mesh phasing in transmissions and assembly and manufacturing errors. On the side of the gearbox housing, as we can see here, detailed vibroacoustic analysis can be done in order to optimize the system, in order to add the ribs where needed, in order to give good NVH performance. Here a reference from Hyundai Mobis, which uses our solutions for edrive engineering. And this is on the transmission side. We have applied our GDO method and working with Mobis to deploy these SimCenter solutions using SimCenter 3D, using SimCenter heats. That allowed them to do a design iteration much faster than what they used to do before. So from 14 to 3 days to analyze, optimize the layout and optimize the gearbox. Let's now go to the last part of the webinar, where we will discuss about integration issues, still looking at NVH as one of the performances to manage. Look into the performance at the vehicle level, and also introduce some more testing capabilities, including model-based edrive testing, and how we can implement these in a simulator. So the idea of analyzing the integration of the eDrive in the vehicle is the following. We are using the source transfer receiver model. And the idea is that at each stage of the development, if you are OEM or supplier, you can have a view about the full vehicle performance. The source representation as well as the transfer in the vehicle can both be represented either by testing or by simulation. And then the system allows to understand the response at vehicle level. There are a few technological considerations, in particular on how to represent the source and in which boundary conditions, in order to avoid that we evaluate the source with different boundary conditions than in the vehicle, and we don't capture the correct response. So for that, we are using blocked forces, which allow to have an invariant representation of the excitation, and then to combine it with the transfer function at the vehicle level. So this approach is available in our virtual prototype assembly tool. And the idea of virtual prototype assembly is to put the different parts of the organization together in order to have the right data to be able to predict the NVH performance, but that also includes collaboration with the suppliers. So the specialists will create a library of components which are integrated in the vehicle, and the assembly is done in the virtual prototype assembly or VPA tool in a SimCenter test lab, which then can be used by analysts to analyze the response, to analyze the contributions, to assess sound quality, but also this data can be used inside NVH simulator and can be used to assess the effect of control strategy. Here you find some examples of typical data sources in order to populate this virtual prototype assembly. So we will define accurate components. We will use a library of components from simulation and or from testing. For instance, test lab data, SimCenter 3D, SimCenter AimSim can be used, as well as external data from other software. Once these component models are created, they are selected for the specific architecture, and then the assembly is done and we can post-process the results. We haven't talked a lot about testing so far, although testing is of course always considered and always very important along the full development cycle. So what we see here is a real intelligent testing setup or model-based NVH testing of an electric drive. You can see here above the eDrive itself, the physical eDrive, which is driven by a motor, and then below you have a real-time computer which has a real-time model of the vehicle running. So the idea is that with this we are able to represent real driving scenarios and to test the NVH of the gearbox along with realistic loading conditions and scenarios. So you can listen to the noise here. See the real-time computer with the AimSim model running in real time. Here we are instrumenting based on CAD, defining the instrumentation, and then processing the data. So here we can illustrate the multiple possibilities within test lab to process the measured data, look at color maps, look at time data, and use different post-processing capabilities in order to understand some NVH phenomena, such as operational deflection shapes, for instance. So you can see the test lab environment, the various post-processing capabilities, present all data as needed. We can also analyze the operational deflection shapes in order to better understand specific noise phenomena. Looking now into the final stages of the development, here is a very nice example and reference with the Hyundai motor of applying our simulation technology in order to evaluate some strategies in order to reduce the noise level. The strategies are linked with the inverter control. Here we are injecting some harmonic in the input current in order to reduce the NVH response. So this strategy is evaluated by using the eNoise app in order to come up with a very fast prediction, so to really optimize the strategy. So here the key in this collaboration was the involvement of our engineering services to bring this workflow to customer and to allow him to test different strategies with a very nice results and outcome, as we can see on the graph with the NVH reduction. We now come to the conclusion of this webinar, and for this I would like to come back to the initial representation of the different stages of the development, which allow us to highlight how we deal with NVH, which are our simulation and testing solutions for NVH, but also looking at multi-attribute balancing, and also how this is integrated into the product development process, such that the requirements defined early on in the program can be followed up through the program, and we can check the performance predicted first by simulation, then by testing, or a combination of simulation and testing, and compare that with the requirements to make sure we are on track for the program. So our engineering services are available to support you using our product. We can propose dedicated services in order to make sure that you leverage the SimCenter product and to create workflows which are fit to your needs. Finally, I would like to refer to some other sources of information. So don't hesitate to go in our website. Also, you will be able to download this material and have the links to our different solutions for NVH, for electric drive, and for automotive industry in general. So I would like to thank you for attending this webinar, and we will be happy to answer questions. So don't hesitate to contact us, Jonas and myself, in case you have questions, and we will see that we can support you. Thank you. Goodbye.